Good morning to all of you. Today we will discuss sampling rate conversion of bandpass signals. Okay, so till now what we have seen is how to convert low pass signals, and in today's class we will discuss how to convert sampling rate convert of bandpass signals. First we will see what is the difference between low pass signal and bandpass signal. Low pass signal means if the frequency content of the spectrum is centered about origin or zero, it is called a low pass signal. Bandpass signal means if the signal spectrum is centered about some frequency which is non-zero, it is called a bandpass signal. Okay, so how to convert this bandpass signal from one sampling rate to another sampling rate, that we are going to see in today's class, and what is the process and how to convert it and what are the devices available and where we are going to use this sampling rate conversion of bandpass signals we are going to see. Generally, in most of the communication systems, we will use such type of sampling rate conversion of bandpass signals, because as we know that speech signal spectrum is occupied from 0.3 kHz to 3.4 kHz. That is the spectrum of speech or audio signal. And if you want to send this signal as it is without modulation, generally it is not possible. So that is why there are different reasons are there why we cannot transmit low pass signals. Okay, and that is not in our scope right now. And generally we modulate the low frequency signal to high frequency. That is nothing but modulation. So when you shift it or translate the low frequency spectrum to high frequency spectrum, that is called frequency translation. So most of the voice signals, sometimes even most of the image and other video signals, they are low pass signals. And if you want to transmit that signal, we have to translate that low pass signal to a band pass signal. And after band passing, after converting to the high frequencies, then we have to transmit the signal to the channel. And channel, after travel, means after propagating through the channel, finally it is received at the receiver. So now in most of the mobile communication, so we use this sampling rate conversion of band pass signals. Almost all every communication we are going to use this. Okay, now we will see how to implement this sampling rate conversion of band pass signal. Okay, first we understand the spectrum of low pass signal. Okay, so the spectrum of low pass signal is like this. Drawing here, spectrum of low pass signal. Suppose this is a frequency domain. Spectrum means we know that it is a frequency domain. Now you see this is origin W and minus W 0, and you assume that this is the X of F. Okay, X of F is the spectrum of the signal, and this spectrum is occupied from minus W to plus W. So therefore this spectrum of X of t is centered about the origin. That is why we call it as a low pass spectrum or low pass signal. Low pass signal spectrum. Okay, low pass signal spectrum. So what is the low pass signal spectrum? If the frequency content of the signal is centered about the origin, then we say that it is a low pass signal spectrum. And band pass signal spectrum means it looks like this. Band pass signal spectrum. Okay, now see Suppose if the spectrum is centered about Fc and Fc plus W, this one, and this is Fc minus W. Now we assume that this is X1F, this is X2F. The spectrum axis is frequency axis. Now this is called a band pass signal spectrum. A pass band pass signal. Okay, I hope you can differentiate what is the low pass signal spectrum and band pass signal spectrum. So if the signal spectrum is centered about the origin means 0, it is called low pass signal. Second one is band pass signal. Band pass signal means spectrum is not centered about the origin. This is the origin 0, okay, and the spectrum is centered about Fc. Fc is a non-zero value. Fc is some non-zero because this is a 0 origin. Fc is some high frequency. Fc means center frequency. So the center frequency is some high frequency which is not a 0 value. So therefore this is called a band pass signal, a band pass signal spectrum. Okay, so this is a low pass signal spectrum. This is the band pass signal spectrum. Band pass signal means a signal whose spectral components are centered about some central frequency which is not a 0 frequency. Okay, so now you can clearly understand from these two diagrams the two spectral components. Now we have to convert this type of band pass signal. We have to convert sampling rate conversion of band pass signal means we have to convert such type of band pass signal. We have to means like we have to convert the sampling rate of this signal, not this one. We have seen sampling rate conversion of low pass signals so previously in the beginning classes. Now we are going to see this. Now to implement that, to implement the sampling rate conversion of a band pass signal, now we have a block diagram for that. Okay, sampling rate conversion of band pass signals. This is the first block diagram is there. That is the block diagram representation, block diagram of a system of representing sampling rate conversion of band pass signals. First of all, we have a band pass signal X of n. Okay, that is a band pass signal, which means what you have to understand is X of n is already it is a band pass signal. Okay, so now, so the band pass signal is applied to this frequency translation. Now what frequency translation means? So shifting the frequency from band pass to low pass, otherwise changing or translating the high frequency or band pass signal to a low pass signal. Okay, so that is what happens in the frequency translation block. Inside the frequency translation block, we have a such type of arrangement. See this? So this is a conversion of band pass signal to low pass signal. So therefore, conversion means what? High frequency, converting the high frequency to low frequency. Because see, this is central frequency Fc here. Now this Fc low pass means it is shifted to the 0 frequency, means center about origin. Now that is performed by this block diagram or system. Okay, now we apply the band pass signal here, X of n. Now same X of n comes here, same X of n. Here also X of n comes here. Okay. Now X of n is multiplied by cos 2 pi Fcm here and sin 2 pi Fcm. Okay. So because this is an oscillator which oscillates or which generates the quadrature components. Quadrature means so cosine and sine, they are called quadrature because they are differed by 90 degrees phase shift. So therefore this, after applying this X of n, this is a multiplier. Okay, this is a multiplier. So multiplier means which multiplies the input signals. Input signals which are applied to this. This is also multiplier. Now X of n cos 2 pi Fcn, these two are multiplied and they are available here. And so whenever if you multiply two frequency components, you will get higher order frequency components. Suppose see, If you have so x of n is cos 2 pi f1 n, in the same way cos 2 pi fcn, then what happens is you will get fc plus fn, fc minus fn. Like that, whenever if you multiply is nothing but modulation. When you modulate the signal, then what you will get is you will get a product terms. In that product terms, you will have a higher order frequency components. So to remove that higher order frequency components, we will use a low pass filter. So low pass filter in both the cases. Here also same, we apply a band pass signal here. That band pass signal x of n, and that x of n is multiplied by the sin 2 pi fcn. That is the carrier frequency, like a center frequency or carrier frequency. And when both these input band pass signal and this carrier, they are multiplied, and you will get again in the bottom branch also you will get some higher order frequency components. So to remove the higher order frequency components, we will use a low pass filter. So therefore UCN and USN, these are called quadrature components. After low pass filtering the sequence, we get UCN and USN. Okay, UCN and USN, they are quadrature components, and these quadrature components now we can see from this block diagram. After frequency translation, to frequency translate, the main operation is multiplication. Multiplication is nothing but modulation also. So therefore, once if you multiply this original band pass signal and this carrier, you get a signal, and that signal, in that signal we have a low frequency and high frequency content. Remove the high frequency content, preserve the low frequency content. Here also same. So therefore, now UCN and USN, these are the two quadrature components. UCN and USN, these are quadrature frequency components. Okay, quadrature frequency components. They differ by 90 degrees angle, you can understand this. Now after that, so this is a interpolator, as we know already, we have seen from many classes. So this UCN and USN are upsampled by L, factor L, because now what happens is, you see, this is the spectrum of band pass signal. Spectrum of band pass signal. So where M is some integer M is some positive integer. So this capital M is that decimating factor. Capital M is the decimating factor. Now see, whenever you have a band pass signal like this, and this band pass signal spectrum, then it is upsampled. So then what happens in the upsampling? Whenever if you upsample the signal, so zeros are introduced, or multiple copies of the spectral components are introduced between the two adjacent spectral components. Suppose if you have a L sampling rate converter, like interpolating factor L, so then what happens is, so you will have a L minus 1 copies are inserted between two adjacent spectral components. Okay, that is what happens here. Now what to understand is, already this UCN and USN, these frequency components are converted to low frequency, because we will perform the sampling rate conversion only on the low frequency, but initially it is a band pass signal. Initially it is a band pass signal, and whose spectral components are not centered about origin, because you can understand, so this is 0, so this is the origin, and this spectrum is centered about from m pi by m to m plus 1 pi by m. So therefore, here already the signal is converted to the low pass signal. After low pass conversion, then we do the upsampling. After upsampling, we have a filter. This filter is a combination of both, like anti-imaging filter as well as anti-aliasing filter. Okay, so this filter is anti-imaging and anti-aliasing. What it will do, anti-imaging means whenever multiple images are there, so you can remove any unwanted images. In the same way, Anti-aliasing means if you have any high frequency components which are not suitable for your application, you can remove it. So therefore, this filter will have the two functionalities, anti-imaging and anti-aliasing filter. So both are integrated into a single block, and the output is down converted. So output is down converted means then what happens is, so if M is 2, then what happens, 2 minus 1 samples are discarded. 2 minus 1 spectral copies are discarded between the two adjacent spectral components. In that way, so we can convert any bandpass signal to, we can convert from one sampling rate to another sampling rate in the bandpass signals. Okay, here the idea is very simple. The idea is if you want to convert one frequency sampling rate to another sampling rate of a bandpass signal, first we translate that high frequency signal or bandpass signal into a low pass signal using the frequency translator block, this one. After after converting to the low frequency, then we apply the interpolator and decimator. Like it is a cascading connection only. We have seen the cascading of sampling rate converters in the previous class. Same thing, right? We are cascading interpolator and decimator one after other. So that is why. So finally we will have a curve down means conversion of the sampling rate signal occurs here. So then now mathematically, if you want to analyze this, you see a bandpass signal x of t is AT cos 2 pi FCT plus theta t. So where AT is the amplitude of this sequence signal, and theta t is the phase angle of the signal. Phase angle of the signal. Now, so cos A plus B. So if you open this bracket, AT cos 2 pi FCT cos theta t, cos A plus B, cos A cos B minus sin A sin B. Okay, the same. So we are using cos 2 pi FCT cos theta minus AT sin 2 pi FCT sin theta t. So now this AT cos 2 pi cos theta t is represented by UCT, right? One component, quadrature component, and AT sin theta t is represented by UST. Okay, so this is a representation of the signal in the form of quadrature. Okay, UCT and UST, that is nothing but representing the signal in the quadrature components. Now this can be written as a real part of XL. XL represents this XLT is equal to UCT plus UST. Okay, UCT plus UST. So this is a low pass representation of the signal. Then this XLT, if you substitute, you will get the same thing only. So because e power j theta or e power j 2 pi FCT is equal to cos 2 pi FCT plus j sin 2 pi FCT. Okay, this is the 2 pi FCT. Okay, sin 2 pi FCT. So therefore, so this is the expansion of this exponential factor. E power j 2 pi FCT is cos 2 pi FCT plus j sin 2 pi FCT. So like that you can mathematically say, now whenever if you multiply with this cos 2 pi FCT, because cos 2 pi FCT is there, what is UCT? UCT is AT cos theta t. So whenever if you multiply it, then what happens? Cos A cos B, cos A plus B plus cos A minus B, like that you will get, and you will get one high frequency component and one low frequency component. And that high frequency component is filtered by this low pass filter. And in the same way, the second term also, UST means what? Sin 2 pi FCT sin theta t. So when if you convert it into addition A plus B forms, then you will get one high frequency component and one low frequency component. And you can remove the high frequency component by using this low pass filter. So like this, we can remove the unwanted signals or high frequency signals which are centered about some higher values. Then we can remove it. You can get the final US of n here and UC of n here. So in this way, we can convert any band pass signal to the low pass signal. After converting into the low pass signal, then we can we can convert the sampling rate of that particular sequence. Okay. So the L means interpolating, M means decimating. Okay. Like that we can convert from one sampling rate to another sampling rate of a band pass signal. Okay. So this is what happens. So suppose this is a very important topic. Even you get university questions on this for 10 marks. So therefore you have to first you have to draw this block diagram. You have to explain what is a band pass signal, what is a low pass signal, and how to convert a band pass signal to low pass signal. You have to draw this block diagram. After that you have to explain how the band pass signal is converted to low pass signal, and after converting the low pass signal you have to explain what is interpolation, what is this filter, and what is the decimation. Okay, in this way, so we can perform the sampling rate conversion of a band pass signal, and finally we get the sampling rate. Now, so we will see the sampling rate of band pass signals. Okay. Now we know from the beginning, like in the second year we have studied in signals and systems, what is the sampling rate of low pass signal. So sampling rate means generally, so if you want to sample any signal like audio or any signal like video signal, so the condition is there. Based on that we have to sample the signal. That is the Nyquist criterion. So what is that Nyquist criterion? So if FM is the highest frequency signal, then if you want to sample that, then we have to sample that signal at least by 2 FM. At least by 2 FM. Sampling frequency must be greater than or equal to twice of the highest frequency component of the signal whichever you want to sample it. Okay, that is the normal sampling rate of any low pass signal. Now there is a little bit difference is there to find out whether sampling rate conversion of this band pass signal is same or not. Definitely it is a different. And now if you see this is a band pass signal which is centered about some frequency, not 0. Okay, because if you want to find out the center frequency, you can take that. So 2 plus 1.5 divided by 2, you will get that. So center frequency. Now if you want to sample this, because see just now we have seen how to sampling rate convert a band pass signal. So first of all we have to understand means what is the sampling rate of band pass signal. How to find out the sampling rate of band pass signal. So there is some steps are there. In the first step, right? First you will see procedure to find sampling rate. Procedure to find the sampling rate of band pass signal. Band pass signal. Okay. So if you want to sample a band pass signal, so we have a different criterion, different like what must be the sampling frequency. So to find out that, first you find the bandwidth of the given band pass signal. So bandwidth I use to represent, I use B to represent the bandwidth. Bandwidth means what? High frequency minus low frequency. Okay. First you find out the bandwidth. After calculating the bandwidth, second step is you find out some factor, that is a constant factor. K is equal to highest frequency FH divided by bandwidth. This is the K value. So K is some positive integer, K is some integer. Like we have to consider integer only. Integer part only. Suppose see, when you do this fraction is like division, if we get k value, so we have to consider only the integer part of that. And after that, now we can calculate the sampling rate of the band pass signal. Okay, sampling rate. We know that sampling rate is represented by Fs. Fs is equal to 2 times of highest frequency divided by k. Okay, so this is the formula to calculate the sampling rate of a band pass signal. Generally, this is a 3 steps procedure is there to calculate the bandwidth of sampling rate of a band pass signal. Okay, now we'll take this example. We try to find out the sampling rate of this band pass signal. First, you have to understand that this is not a low pass signal; it is a band pass signal. So, band pass signal means the signal is centered about some higher value of frequency, not 0. Right? So, here this frequency is not 0; it is somewhere around between 1.5 and 2. So, then this is called, we can say that it is a band pass signal spectrum. Now, see, if you calculate for this, if you calculate this, okay, I will erase this and write here only. Now, first, what we have to find out? We have to find out the bandwidth. So, before calculating the bandwidth, we have to see what is FH. FH is 2 megahertz. FH is 2 megahertz. FL is 1.5 megahertz. This is the frequency, high frequency and low frequency, 1.5 megahertz. Now bandwidth, if you want to calculate the bandwidth, so FH minus FL. FH is 2 megahertz and FL is 1.5 megahertz. So megahertz means you know that it is a 10 power 6 hertz. Now, so 2 minus 1.5 means 0.5 into 10 power 6 hertz. And in terms of kilohertz, so we can write it, so 500 kilohertz. Okay, because 10 power 3, if you take 10 power 3 separately, you can multiply, you will get it 500. So therefore, bandwidth of the bandwidth of the band pass signal is 500 kilohertz. After calculating this bandwidth, now what to do is, so we have to find out this k. Calculate k value. What is k? K is equal to highest frequency divided by bandwidth. Highest frequency, what is highest frequency? Highest frequency is 2 megahertz. Okay, 2 into 10 power 6 divided by 500 kilohertz. 500 into 10 power 3. So now, see this. 2000, we can write 2 megahertz like 2000 kilohertz divided by 500 kilohertz. So this 10 power 3 will get cancelled and 2 zeros, and now here k is exactly 4. The integer value k is exactly. Sometimes what happens is you will get a even fractional value also. So suppose say here you get 20 by 5. Sometimes you can have 1 by 4 or some 10 by 3. Like that you may get different values when you divide this fh and b. Then in that case we have to consider only, suppose say if we get some 4.3, you have to consider 4, like that. Suppose if you get 5.1, you take 5. Like that we have to consider k value always integer only, integer part only. Consider always integer part, and using that k you can calculate the sampling frequency. Now we have to calculate the sampling frequency. So it is simple. Fs is equal to 2 times of fh. 2 times of fh means highest frequency is 2 megahertz. So therefore 2 into 10 power 6 divided by, so this k value is 4. K value is 4. So therefore what happens here? What you will get? 1 megahertz. 1 megahertz or 1 into 10 power 6 H, because see, it's 2 into 2 4 and this 4 will get cancelled. 1 into 10 power 6, that is called 1 megahertz. Now this is the sampling rate of a band pass signal. Sampling rate of a band pass signal. So now if you compare it, so directly if you calculate with the 2fs, you will get a 4 gigahertz, 4 megahertz, not gigahertz, megahertz. But so if you use a band pass signal in this criterion, band pass sampling, we get a 1 megahertz. So that is the difference between sampling rate of low pass signal and sampling rate of band pass signal. So in this way you can calculate. So therefore always there is a limit is there, like bandwidth must be in between. So this maximum value, see 1 megahertz is there. 1 megahertz sampling frequency. If you want to sample this band pass signal, you will have a sampling rate as minimum as 1 megahertz. So therefore there is a always you have to consider this procedure to calculate the sampling rate of a band pass signal. Okay. So even you can observe this. If you take the low pass signal formula, that is directly 2fs, 2 times of fm. Fs is equal to 2 times of fm. So here highest frequency is 2. So therefore if you multiply by 2, then you will get a 4 megahertz. That is incorrect with respect to the sampling rate of band pass signals. Okay. If you want to compute the sampling rate, so first you calculate the bandwidth, then you find out the k value. K is some integer, and after that sampling rate fs is equal to fh by k. Okay. This is the procedure how to convert a band pass signal, means how to find out the sampling frequency of a band pass signal. Using the sampling frequency, if you sample this signal, then only we get the then only we can reconstruct the signal without any noise. Otherwise we may get some aliasing noise in the signals, output signal. Okay. So therefore whatever we have seen in the previous block diagram, in that block diagram, so this process is important. First identify the what is the band pass sampling frequency. After identifying the band pass sampling frequency, then you sample it, and that signal you send it to the frequency translator. Okay. So with that the 5th unit is completed, and if there is any other topics remaining, so we'll see that in the further classes. Thank you.